Thanks for coming to my talk. It's, I guess, the last talk of the day, so that's always fun. So thanks for sticking it out. I'm going to talk about a bunch of research today. So, there's not going to be some Scala library at the end of the talk that you can install and use immediately, unfortunately. But what I'm going to do is kind of just challenge you to think differently about the way you build large-scale distributed applications today. And so my name is Christopher Meiklejohn. I'm a Ph.D. student at the Université Catholique de Leuven in Belgium. This research I'm going to talk about today is a joint research project funded by the European Union. That's work between my university, the HasLab in Portugal, and the University of Oxford. So this is where all of our collaborators are. And so basically the challenges that we're trying to address are how to safely build large-scale systems that minimize coordination. So we're trying to kind of do the opposite of what you might do today, where you build a large-scale distributed system around something like Zookeeper or Consul or etcd or something like this, like a consensus protocol. And so I'm just going to kind of set the stage about what my research works on. And so if we consider the case of an application where we have a register, so a register is like a variable that you can set or get the value, and we distribute this, so we have two copies of it, replica A and replica B. So we distribute this for fault tolerance and high availability traditionally. In most schemes that use optimistic replication, we'll set the value to 1, and then we'll send a message asynchronously to replica B, and we'll say, your value should now be 1. And so at this point in time, the value of B will be 1 as well. Now, without synchronization, without coordination, if I concurrently set replica A to the value 2, and then, in concurrent logical time, I set replica B to the value 3, then at the end of this execution, I don't know what the result I'm going to have is if I do this without coordination. And it's because these messages can be arbitrarily delayed, they can be reordered, and they can be replayed, because this is the realities of the asynchronous kind of communication networks that we build systems on. And so historically, the way that we solve this program, whether you realize it or not, is through the use of synchronization. And so what synchronization does in programming is it enforces an order. It says that given this program, I'm going to enforce either a locking order or some sort of mutex strategy or something like this to enforce a predictable order. And then I know what the outcome of the execution is going to be. And so to kind of put this in non-academic terms, well, first I'll put it in the academic term. We call this accidental non-determinism. But you may be more familiar with the term race condition. It says that if I have a shared object and I am modifying it from 2 actors, I don't know what the value is going to get unless I use a lock to use something like mutual exclusion or something like that. And so the techniques you might be familiar with for solving this problem, there's a bunch. So you have all the traditional concurrent programming techniques such as locks, mutexes, mutual exclusion, semaphores, monitors, and a variety of others. And so in the distributed context, we would have things like Paxos or replicated state machines or things like this. And so the problem that we're looking at as researchers is this situation where if we have devices that are not connected to the internet all the time and they need to continue making progress, if I have 2 devices that are modifying the same piece of data, I can't stop the world and synchronize if the device is offline, because I may wait for an unbounded amount of time. And so in a lot of these cases, and these are motivated by actual industry use cases, in a lot of these cases we cannot use synchronization to solve these problems, and so we need to approach the problems in a different way. And so the example I'm going to give you is based on a company that I've been working with in the Bay Area that monitors the temperature of hospital refrigerators at hospitals around UCSF, so the University of California at San Francisco. And so what they want to do is they want to send alerts whenever the temperature either gets too hot or too warm, because it means there's some sort of manufacturer, like some sort of problem that needs to be addressed by a manufacturer or something like this, like compressors not working or something. And so in the world that we live in today, the way we would kind of address this is we would have our refrigerators and we'd put them on the internet because it's the Internet of Things. And if this is 2007, the architecture that we would use looks kind of like this. We would send data from the refrigerators to some central data center. This data center would be running Hadoop or something similar. And then we would periodically run jobs to say, are any of the refrigerators going bad? And if we found one that was going bad, we'd trigger some alert. Now, That was 2007. It's 2016 now, so things are much more advanced, and so maybe we would use something like Spark or Spark Streaming, right? And so kind of the same idea works. Even if you use Spark Streaming, it's still micro-batching, and so kind of the same philosophy applies. And so in the ideal execution of this application, what we have is that we have our refrigerators, and we'll assume that we're using Spark, and we generate some data point that says things are okay from this refrigerator, and we send it to the data center. Nothing happens. Now, when we generate an alert that says, oh my God, the refrigerator's too warm, everything is going to go bad, then when we transmit this to the data center, ideally what this is going to do is trigger some sort of condition based on some job that's running in Spark, and then it's going to alert somebody on the phone via PagerDuty or something like this, right? And so the interesting observation, if we look at this infrastructure, is that this typical infrastructure relies on immutability. It says that every single event that's generated is unique, and I propagate that event. I can replay these events because there's only ever going to be one with a unique identifier. And so the observation here is that immutability is really expensive because what we're doing is we have these devices that are theoretically low power, but they have to stay online all the time, and they have to operate the antenna all the time because they're constantly transmitting data every second saying everything's fine, everything's fine, everything's fine, until there's a problem. Now, the second problem is if we look at this infrastructure and we consider the case where the internet connection is down for the refrigerator, now we can't transmit the samples. And so a lot of manufacturers will tell you, well, that's fine. What we'll do is we'll buffer them, and we'll eventually transmit them. But in the event that this internet connection is down for, I don't know, a day or an hour, who knows, that might be too late. We may need to take local action here. If you've looked at this research paper that Google released at SIGCOM a few weeks ago, Google at least saw the observation in their own data centers that network partitions that cause connectivity to not work in their own data center would be no quicker resolved than 10 minutes. So, I mean, that can be a big deal if we're talking about, across the whole internet, if we're talking about this is operating over a radio or GPRS or whatever. And so, ideally, what we want to do is we want to be able to have the devices take local action. So we'd like the code that we write that runs over here to also run over here. And this means that when we do this, the devices can continue to take action, continue to process things, even in the event that connectivity is down. So we're decentralizing the processing. And so kind of the observation you can take away from this is that centralized processing isn't available. And when I mean available, I mean availability in kind of the cap big A availability sense in distributed systems, in that the system cannot make progress. It's not live when the connectivity is down. So a lot of this stuff isn't new. This kind of falls under a broad range of research called edge computation. It basically means that we want to push code and the data that code operates on kind of to where the data is being generated, which we refer to as the logical extremes of the network. Ideally, we want this to be arbitrary computation, so anything that you could run on a Turing machine, anything kind of like that you'd want to be able to do. We'll see that that's not easily able to be done. And finally, there's precedent on a lot of this work going back for a very long time. There's systems, at least in the 80s, that did some of this stuff. And then in the 90s, Cornell University in the United States did a lot of work around having self-organizing systems that were used by the US military in areas where there was only peer-to-peer connectivity and transitive connectivity between peers. You couldn't rely on there being Wi-Fi, effectively, in the battlefield, right? And so what I'm going to try to convince you of, I guess, or rather, the point of my research is that the ideal, the gold standard we consider here is that all of the devices, rather than transmitting individual events saying what the state is over time, a time series, what I want to convince you is that, well, what we could do is just keep a piece of state that represents the state of everything, and then we could transitively disseminate this without order to all the clients in the system. And effectively, what this will allow us to do is have any of the events in our system, any of the machines in our system take local action. And what I'm representing here is that the core challenge here is that traditionally in systems, like I said in the beginning, we need synchronization to enforce a predictable order so we can program against that order. And what I'm trying to do with my research is build programming languages and computational models where ordering doesn't matter. And we'll see what I mean by that. And so again, to summarize the 2 points of the research, the 2 points are that immutability is very nice, it's very easy to program, but it's very expensive. It's very expensive in terms of bandwidth, and because it's expensive in terms of bandwidth, it's expensive in terms of power, because we have to operate antennas on devices. And the second one is that centralized processing is not available, but it's easier to program. And so can we make distributed programming as easy as centralized programming? Now, to just kind of give you some figures so you understand what we're looking at here, if we look at this report from Andreessen Horowitz from a deck they released, I forget, maybe earlier this year or last year, we can see that even though the price to manufacture mobile devices is getting much cheaper, and mobile devices are becoming kind of, everybody has one, they're everywhere, we can get them to all sorts of countries, we see that data is still really expensive. And so the price of bandwidth and the price of data is not going down in the same way that kind of Moore's law is affecting our processing. And so the goals of my work, to summarize, are to make mutable state as reality. So can we make dealing with mutable state easier? And secondly, immutability makes programming easier, so can we make programming with mutable state in a distributed system easier? And so these are challenging because it relies on commutativity, and we'll talk more about how commutativity plies in with concurrency. And so the goal of researchers, again, is to just kind of combine these two things and see how far we can push it. And so if you're not familiar with distributed programming, and you're familiar with concurrent programming, the main difference when you move from concurrent programming to distributed programming is that in distributed programming, things can fail and you don't know that they failed. So in a lot of concurrent programming models we have today, assume that you can reliably detect a failure. You kind of have, and you have synchronized clocks on your machine, right? And you have a clock rate on your machine. And so distributed systems brings in this additional challenge that I could send a message to somebody, and I don't know if that party received the message and didn't reply, or never received the message, or received the message and crashed. And I cannot determine the difference of these things, and there's a lot of famous academic results that show that this is extremely difficult to do reliably, and so we need to build systems that do this in an unreliable fashion. And so timeouts are one way that we do this in real systems that's unreliable, because we assume if you didn't respond within this time, you're down. But that doesn't mean that you're actually down. And so the reason that this is challenging is because traditionally in distributed database development to date, what we do is we build these massively big databases that have hundreds of machines, but in these systems what we try to do is give the illusion that they are one system with one consistency model. If I write to one machine and I read from another, I'll get the same value. And we'll see that that's very difficult to do in practice. So to show you kind of where synchronization plays in and why it might be unreliable, I'm going to talk about databases. And so prior to doing my Ph.D., I was an engineer I worked on many databases. I worked on a database at a gaming company, Machine Zone. I worked at Basho for several years on the React database. And I also worked at Mesosphere on their database that is used for high availability in Marathon. And so a lot of my background is on databases. And so I'll briefly talk about databases. And so in databases, we have this notion of linearizability, or more commonly known, strong consistency. And what this means is, if I have a single copy of my database, so only one replica, and I have this object, this green circle, if I have two clients that are executing concurrently, one is going to read a value from the replica, and then the second node is going to read the same value from that replica. Now, when client one mutates this value and changes it from the green circle to the blue square, when client one goes to write this operation back to the database, a lot of times we use what's referred to as a compare and swap operation, which says that as long as the value is still the green circle, my change of that value to the blue square is still valid. But if that value changed in between the time that I retrieved it and wrote a value and sent it back to the database, I want to refuse that operation. So this succeeds. But then when client 2 goes to write its red diamond back to the replica, this operation fails. And the reason this is done in a lot of databases is, and transaction protocols kind of work this way if you're familiar, depending on the isolation level and the consistency level it provides. But the intuition here is that, well, my change of that value to this red diamond might no longer be valid because I based my change on some state that is no longer in the database. Now, you can imagine if I have to do this in a distributed system where I have multiple copies of my replicas, multiple copies of my database, multiple replicas, and any of them can arbitrarily fail, and I want to maintain availability, you can imagine that this process gets very, very expensive. Because now I need to have the nodes agree on what the value is going to be, and I need to wait until I have acknowledgments from a majority of those nodes, and then I can proceed. And so we're starting to see kind of Amdahl's law come out here, where we only can go fast as the slowest kind of component here, which is going to be solving that consensus problem, getting agreement of these databases. And so you may be more familiar with databases, these web-scale databases that have an eventually consistent or a weakly consistent model. REAC is one of these. Apache Cassandra is another. And the way these databases work is they kind of acknowledge that you're going to have concurrent readers and writers operating, but then concurrently, client 1 could go to issue a write back at the same time that client 2 goes to issue a write back. And because of this, what a lot of these databases do is they'll store multiple values back because they cannot determine a relationship between those values. They say they happen concurrently. We don't know which one really happened first. And so they'll store multiple values and they'll place the onus on the application developer when they read the database next time to resolve these. And so if we go back to the Apache, so REAC will store both because it never wants to lose a write. If we look at the default settings for Apache Cassandra will use the last one that happened at the timestamp provided by the client. And so in the REAC case, you have to deal with the problem where you have multiple values, and when you read from the database, you might not be expecting multiple values. Where in the Apache Cassandra case, what you can do is you can supply a timestamp that's much farther in the future than it actually is, and then no write that will ever happen after you in actual temporal time until that time is reached will appear. Because you've effectively said, I wrote this in the future, and so it's going to be there until it gets to be that time in the future. And so Cassandra resolves this automatically, will arbitrate and pick the one with the greatest timestamp. And so kind of both of these approaches are problematic because it makes developing on these systems difficult for application developers. And so we're going to kind of argue with this work that weak consistency is a better model because this concurrency actually happens. To assume that you can have a total order on a globally distributed system for every single event that happens anywhere in the world, well, that's kind of a fallacy, right? There is no simultaneity plane. We can't do this. It makes programming easier, and that's why we do it. But it doesn't actually match the way things are actually working. And so to resolve this, the area of research that me and my colleagues work on is an area of research called strong eventual consistency. And so this is a combination of a convergence property, which is strong, and a consistency model, which is weak. And what this says is that as long as all of the machines in the system observe the same set of updates, regardless of order, they'll all converge to the same result. Now, what's nice about this model is that it only relies on us delivering the messages to every node in the system. This can be done transitively. You don't need a sequencer. You don't need consensus. You don't need anything like that. And the other very two important properties demonstrated from my earlier example are that since all the operations with strong eventual consistency systems are commutative, that means I can deliver the updates in any order, which is very nice. The other benefit is that there's also operations are idempotent, so I can replay them multiple times. So I can build systems that are at least once delivery, which is nice because those are easier to build. And finally, it's also batching insensitive, which is an associativity property if you remember your high school algebra. And so I'm going to give you a super simple example of kind of how we could fulfill this trivially that won't be super valuable. So if we go back to the original example that I had here, I said that I was going to concurrently write 2 and 3 to this register. Now, if I assume that the values that I only can give to this register are arranged over the monotonically increasing natural numbers, so from 1 and greater, then a function that delivers strong eventual consistency is the max function. It says that I can reorder this diagram in any arbitrary way, and I can replay these messages an arbitrary number of times, and I will not get different results. I will always get the same result. Now, is this useful? No. I mean, if you were building a distributed counting service and charging for API calls, then this would be a really, really great design for that. But this is not very useful in itself, right? And so the challenge that we are trying to solve is, how can I make this max function be arbitrary? How can I make this an arbitrary f, and that f is your application code? And so we'll see that this is extremely difficult to do. That's why you get a Ph.D. for it, I guess. Or maybe you don't, if you don't solve it. And so if we would say, if we go back on the strong eventual consistency idea, if I was going to define a criteria on why I think how we can be successful in building these systems, I would break it into 3 components. And so the first component is we want these data structures that allow us to do these operations without coordination. Now, once I have a bunch of data structures that allow me to do this, what I need is a programming language that allows me to build applications with these data structures. And so we'll see what I mean, but the important property here that we're trying to achieve is something we call confluence. And so if you're familiar with lambda calculus or Haskell programming or something, confluence is a property that says I can evaluate the schedule of a program in any arbitrary order, any arbitrary reduction order, and I get the same result. And that's a very important property to have in programming languages. And then finally, the last component is, well, we need a way to actually deploy this thing and run it because that's the way things work in the real world, and we have to make this efficient. And so we'll talk about the challenges there. Okay, and so I'm going to go through each of these in sequence. And so for number one, for the data structures, the design that I showed you before is a much more general design that was observed by some of my colleagues in 2011. And this data structure design is called conflict-free replicated data types. And so what conflict-free replicated data types are data structures that have sequential versions, but they're designed for distribution. So we have things like sets, counters, registers. So counters are integers, but you can't set the value. You only can start at a particular value and go up and down. Well, that's problematic because set is an operation that is not commutative in many cases. We have things like flags, which are booleans that can move in one direction. So they can move from false to true or true to false. We'll see that's a lattice. And then finally, we have things like dictionaries, which are recursive, and graphs. And so there's also sequences, but sequences are much too complicated to show here. But sequences obviously would be your list data type. And what these data structures are going to do is they're going to fulfill this property, this convergence property, for a given data structure only. And I'm going to show you what this means. So I'm going to show you how to design a set that can be distributed without coordination, or minimal coordination, that will allow me to remove and add elements to it and always get the same result after just doing asynchronous replication. And so the way this works is I'm going to have three pieces here. The circle in the middle is going to represent what the value of the set is at that time. The kind of oval shape on the top there is going to be the operation that I'm running. And then I'm going to model the contents of the set as a set of 3 tuples. And these 3 tuples are going to represent the element that's been added to the set, a set of unique constants representing the times it was added, and a set of unique removals. And so the way this works is when replica A goes to issue an add on the set and add the value 1, it's going to generate some unique token represented by alpha here, and it's going to add 1 with alpha. And so what this representation shows is that I have added 1 to the set with unique at time, logical time, alpha. Now it's going to asynchronously replicate these messages to the other replicas in the system. And now if concurrently replica C also adds 1, replica C is going to generate a different constant beta, and that constant is going to represent that C added it at logical time beta. Now when C goes to remove the element from the set, C is going to take the additions it knows about, so the times it was added it knows about, and it's going to mark them as deleted. So it said, okay, I saw that 1 was added to the set at logical time beta, and so I'm going to mark beta as deleted. Now what happens is when I eventually deliver these messages from A, what I do is to merge these data structures together, I take the pairwise union of both the additions and the removals, and then determine what is in the set. I say, is the additions a strict superset of the removals? And if it is, then 1 is still in the set. And so what this shows here is that it shows here that 1 is in the set because it was added at logical time alpha, added at logical time beta, and removed at logical time beta. And so this allows me to modify a data structure where I can add and remove things arbitrarily, and I don't have to worry about using something like Paxos to coordinate the writes if I want convergence.
Sorry, just one question in your diagram there. Is this the add and remove in the third line here really happening at the same time?
It's happening concurrently, so there's no relationship between them. Because the remove operation tombstones the known adds. Remove happens at a different time, but it marks the additions it's seen as removed. Right. So it says I observe these. So beta there is not the time it was removed. We're not recording this. I am not recording that here. Yes, but there are some representations that do record the time. It's just not necessary for this. Okay, and so that's how you do data structures. And so there's a variety of these. This is a very unoptimized representation because it grows on order of the number of operations that are executed, and so that's not very good. But we have all sorts of optimized representations of this. We have a bunch of variants of this set, and so if you're interested in that, after the talk, I can point you to the literature where there are many, many different designs. This is just the one that's the most compelling for slide-driven development, if you will. Okay, and so once we have these data structures are formalized as bounded joint semilattices if you're into mathematics, and once we have these data structures, what we need is a programming language that will allow us to build applications with them. Because I can't read the value. If I go back to this example, and at this time I read this value and then I base some decision on it in my language, well, when it eventually merges this, that decision might not be valid anymore. And so what we want to do is have a language that appears like a normal functional language, but actually it manipulates all of this internal metadata transparently for you. As you can think of this as kind of a monadic composition of the data structures. And so we built a system in 2015 called Lattice Processing, or Lasp for short. And this is a system that is an asynchronous data flow system that has a functional programming API that allows you to take these objects and compose them in ways. And so the only operations we have today are things like map, filter, fold, product union, and intersection. But this is sufficient for us to express a good amount of a subset of ANSI SQL that allows people to kind of express types of computations that they want to run. And so the important thing here is that the language, the core data abstraction, the only data abstraction in the language is the CRDT. So it's just these data structures we talked about. And finally, what this does is allows us to guarantee SEC through composition. So if I take some data structure and I compute some product and then I filter it and fold it into some aggregate, I guarantee that the result I get out at the end is a CRDT, which means that I can have a CRDT input, a program, and produce a CRDT output. And I can partially execute these. I can merge the results of programs. It's very nice. And so what this looks like is this is pseudocode. All of our prototype is implemented in Erlang. And basically, the most important thing here to just see is that I have some set S1, and I can apply some function here that doubles the elements in S1 and produces the set S2. And just these annotations are all required because Erlang doesn't have a type system. And so what this is going to do is that every time that set changes, because we're replicating things and sending these messages, it will keep those data structures in sync. So S2 will always be the map applied to S1. And it guarantees this monotonicity property. So to go back to the example I had before, if I'm considering this map operation that doubles the elements, if I have replica C, this is the same replica C you saw before with the betas that are being merged, and with the betas that are being added and removed. And then I have the function applied to replica C at the same node. What this is going to say is every time this first data structure changes, I compute some new result for the second data structure. And so this map is pretty trivial here because all I have to do is map the metadata through without changing it and just modify the element. So map is kind of trivial. It gets a lot more complicated when you start doing the other operations. And so we can just imagine that this is an arbitrary transformation process, and then we produce some result where this metadata is combined and munged in the correct way. Now, to talk about this confluence property that I keep saying is so important, what this confluence property says is that if I have this application with data structure A and my map process here, which is really an arbitrary application written in Lasp, and then I have data structure B, which is the result. What I want to do is, as a programmer, I want to write this as if it's a single-threaded application. I want to have an input data structure. I want to have some program that operates over that input data structure. And then I want to produce some output data structure. Now, in reality, what you're really going to do is probably have this arbitrarily distributed across all of the nodes in your system. So there will be a B prime, there'll be a B double prime, there'll be a B triple prime, and you'll have this flow replicated for every node in your system. So every one of these vertical structures. Now, the confluence property that's so important says that if I have a piece of input that comes in through A, synchronizes because A and A prime are synchronized, as I showed you, computes this way and synchronizes out this way, I want to guarantee that for that same input, I can also have the same output if it happens this way. Because with no synchronization, I cannot enforce the order that events are going to travel on the network. The event might travel to my colleague over here, and then my colleague over here, and back to me, or it might happen the opposite way. I don't know. It's going to be based on who's online, who I have connectivity to, and things like this. And so ideally, I want all of these different possible paths to be reducible to this same path. And what this property shows us, what's very important about this property, is it shows us that I can take a program written in this way, which is a very, very small subset of a language. It only allows us to express a few things. But I can say for the very small amount of things I can express, I can arbitrarily distribute the program without sacrificing program correctness. And so that's a very nice property to have, because getting these distribution things is very, very difficult without coordination. Now, you might be saying, these data structures are great, but they're really expensive, and so how can we do this efficiently? And so we're working on a system currently which is called Anabranch, which is a layered approach to building runtime systems for distributed data languages, trying to reevaluate the approach that we take. And so what Anabranch is going to do is it's going to use techniques that we refer to as delta state synchronization that allow us to not have to ship that data structure around all the time. So we can ship a minimal representation of that data. So it's very efficient. And then finally, we'd like to demonstrate that it scales. So currently today, our prototype runs for a single application at 1,024 nodes in the same cluster, which is pretty impressive considering that at least for the Erlang users in the room, the biggest cluster that Ericsson has ever run of Erlang is only 200 to 300. So that's a pretty nice increase. And so our target number by at least in the next 6 to 8 months is 10,000 nodes. So we'll see if we get there. But most of the problems around state dissemination have been resolved pretty easily with some of the techniques that we have. And so the runtime system takes a layered approach at how distributed applications should be built. So the first component is that we need a way to persist the data structures. We need a way for a client to have a bunch of data structures and store them on disk and be able to retrieve them. And so we do this by having pluggable backends that run either via LevelDB or RocksDB or something like this, or can be stored in memory. The second component is that all of the machines in the network in this 1,024 node cluster that I run, all of the machines in the network need to have a way to synchronize with each other. So we need service discovery. And in addition to that, we also want to enforce different types of dissemination topologies. And so our system is configurable to either operate in a client-server mode, where you have this hub and spoke with servers where clients are connecting to the servers, or it can operate in peer-to-peer mode. Excellent.
May I have your attention, please? May I have your attention, please? The public address and fire alarm systems are about to be tested. The fire alert signal will first sound, followed by the fire evacuation signal. Please take no further action. The test is now complete. If you had difficulty in clearly hearing messages or fire alarm signals, please advise main reception. Thank you for your cooperation.
Even they're concerned about drop messages. You hear that? Yeah. I mean, it's amazing. And so finally, if we have particular topologies, if we can make particular guarantees about the network, then we can optimize the network by building spanning trees and doing all sorts of clever things there. And so we have a way to do this as well. And so to give you an example of what the Lasp kind of the Anabranch runtime system looks like, is that we have a unified way of looking at how we deal with mobile phones, distributed hash tables, replicated state machines, any type of system. And what we do is we build an overlay. We have our application, which sits on top of our language runtime. We have a KV store that's built into the runtime for persisting all of the state of your applications. And then we have a pluggable membership layer that controls either operating your system in client-server or peer-to-peer mode. And so this has proved to be a very nice way, because we can kind of swap out components and optimize things and unoptimize things and run all sorts of experiments. Now, the core behind how we're able to efficiently disseminate things in the network is this technique called delta-based dissemination. And so what it does is it uses a variant of these CRDTs that are referred to as delta state CRDTs. And the observation here is that if I have some massive data structure and I only add one element to the set, I can produce a minimal representation of that change and disseminate just that change rather than the entire data structure. So what this allows clients to do is that they operate locally on their own data types, and then they periodically disseminate a buffer to the other clients they know about in the system that delivers the messages in causal order so it can be applied correctly and allow us to have the most minimal representation. Now, the core challenge behind this is that you cannot have a system where every client knows about every other client in the system, because then it becomes too difficult to buffer all of the updates. And so you have to rely on this transitive closure over all of the clients in the system. And so what we do is we have a protocol that underlies our system that builds an overlay network where not every client knows about every other client in the system, and that is a fixed size that approaches log scale. And then what we do is for every time I change a data structure, I buffer an update to the people I know about, I deliver it to them, and then they produce a delta based on that, and then disseminate it to them. So we have this transitive delivery of messages. And so what this looks like is that in this example, replica A performs some change, which is this green circle. I produce a minimal representation of this change, and then I buffer it for the 3 other clients that I know about. Now, there could be 200 clients in the system, but I only know about 3 other clients, and so I only buffer it for those 3. Replica B also does the same. We're assuming that the views are symmetric, and so B also knows the same members here. And then I buffer these in causal order, because if I can deliver these, if I can make a guarantee that I deliver these in the order that they were generated, then the deltas can become even more minimal than they could normally be. If you can deliver them in any order, the deltas get more expensive. And so by making a trade-off with stronger delivery guarantees, you can get a more minimal representation. So when I go to synchronize, all I do is I send these buffers, I apply the buffers, and I flush them, and it's done. And so what we do is we just periodically do this whenever clients are offline, and we actually have a mechanism for quantifying how far off somebody may be from the global view of the system. And so those are kind of the 3 components. And so to kind of get to the last part of the talk, I'm going to talk about one application that we built as part of a research project with Rovio Entertainment, which is the company that makes Angry Birds, as part of this sync-free project that we are collaborators on with Trifork as well. And so we built this thing called the advertisement counter. And so what Rovio Entertainment wanted was the ability to display ads inside of the game. And then these ads would be displayed while the clients were offline, so it would keep track of all the times the ad was displayed. This would happen while clients were offline. And then periodically, they would synchronize this state back at a centralized location. And then what we would do is we would wait for a minimum number of ads to be shown and then disable the ad. Now, can you do this with regular integers? No, absolutely not. And the reason is that if we both have a counter that says the counter value is now 1, and then we both go offline and we both increment that counter to 2, and then we come online and synchronize, that max function doesn't work because that max function is going to give me 2. And that means that I will lose one of the impressions. And so the goal in this design is to ensure that we never drop one of the impressions. And so we do this with a CRDT-based number, which we call a counter, a grow-only counter. And so what we do is we have an application design that roughly looks like this. This entire thing, minus the component at the end, is expressible in SQL now, so it's very nice to write. This is actually just a data flow representation of a SQL query, which has a union, and then a product and filter combination, which is just a join. That's how you express a join, is a product filter with a map. And so kind of the most important part here that I want to demonstrate is that we just say, I have some ads, I have some contracts that say which ads should be displayed. I take an inner join, and then I just select the ads that have contracts that should be displayed. So it's pretty simple. Looks complicated, but it's not. Now what I do is I send a copy of those counters to every single mobile device that's running, and then those counters are incremented by the clients on the devices. And then periodically, those counters will be synchronized back with the central server. And when the central server receives those counters, and can receive this through other clients or directly, it will say, well, when the counter has reached a minimum value, as long as I guarantee I've displayed the ad enough times, then I'll issue a removal, and I'll remove that ad, and then I'll send down to the clients to say, stop displaying that ad. And so I've already shown you how we can do this, because I've already showed you how you can do a removal without having to coordinate. That was the first example I gave you with that set. I said I can remove this thing, I don't have to synchronize for it. So I've shown you how I can capture the removal and capture the dissemination of the state, and I can do this all with minimal coordination. And so, from an academic standpoint, this is a very nice program to analyze because it's completely monotonic. Information only grows in the system. We don't need to have coordination because coordination is needed to retract information many times because you have to get agreement that it's no longer valid. The other thing I've shown you with the confluence property is that we can arbitrarily distribute the application, and we don't have to make sure 2 parts of the application run on one node, because the confluence property says, well, I can just arbitrarily distribute these things. I don't have to worry about the ordering guarantees at all. And finally, an interesting observation that you can make is that depending on how often the clients synchronize back with the centralized server, we can quantify this in terms of divergence. So if we know that clients are only going to synchronize back every so often, we can quantify what the maximum amount we ever might overcount is. And then we can configure clients to synchronize more often if we want to reduce the amount that we overcount, because they're periodically synchronizing. And so you could have a bunch of people that are right at the threshold. They don't synchronize for 5 minutes, and so they might overcount for that whole 5-minute period. And so the general idea here, and hopefully what I've tried to convince you of, is that what we're trying to do is we're trying to look at building applications and adding synchronization just where it's necessary. We're not trying to look at existing systems that are built using Spark or Zookeeper or something like this that you might be more familiar with, and then try to figure out how to make those systems go faster by looking at the things that don't need to happen in order and pull those apart. What we're trying to do is take a look at building applications that gradually add synchronization only where we know that it's going to make the program not correct. We know where it's going to sacrifice correctness of the application. And so what have we learned? So to summarize the 3 points, CRDTs are a very interesting thing. CRDTs have been around the longest, so they exist in many forms. There's implementations in Go, there's implementations in Akka. I know the people working on it in Akka and all the people at Lightbend. So there's a bunch of CRDT stuff happening in the Scala world. There's a bunch of CRDTs happening in the Erlang world from Erlang Solutions and Basho and our research group, which primarily writes in Erlang. So CRDTs are around a lot, and they're a great solution for if you have a single data structure that you want to have, you want to eliminate these concurrency anomalies. Second point is that if you can build applications that have this strong confluence property, building distributed applications becomes much easier. And so what we're doing is growing a language slowly around trying to apply CRDTs to make systems more flexible. And then finally, our most recent work is on the observation that before we kind of make our language able to do more, we have to build a runtime system that allows just what we can do today be very efficient. And so we're working on the large-scale evaluation and making the system actually run well. And so if I want to give you key points to take away for your own system design, I have kind of 3 points to make, I guess. The first one is that it's a reality that many applications today, and continuing to grow, are applications that are not going to be able to synchronize. You cannot have a mobile application that's going to operate offline if you need to totally order every single operation. And you can't allow any speculative execution. If you cannot do that, your application won't be available. I made a joke at a conference once that said, I can't call, the only way I can do this is if I call everybody to tell them to get online, and so we can run around to Paxos, and a good colleague of mine said, well, then all you're doing is solving consensus over the phone instead of on the computer, so I guess that's the point there. The second point is that you should only apply synchronization where it's required. There are some problems that we deal with in computing that are a synchronization problem, so you cannot build them synchronization free. For instance, if you need to enforce strict global invariance, you cannot do this synchronization free. This is a synchronization problem. Second one, if you need atomic visibility on writes in a system, same problem. And finally, I think there's a lot of value in building systems that attempt to take a holistic approach to solving the problem and building up from kind of components rather than trying to take something off the shelf and bending it to fit the type of application you're trying to develop. And so I challenge people to think more holistically about the applications that they're building with distributed systems today. And so to wrap up, I'm going to leave you with this quote from Ivan Sutherland, who I had the pleasure of meeting a couple weeks ago. He won the Turing Award for basically inventing computer graphics. And so he's actually working on a similar thing. He's working on designing hardware without synchronization. So asynchronous systems, no clocks. It's kind of like data flow in the hardware, you can imagine. And so he kind of makes the same observation that I made. We actually didn't even know each other until 2 weeks ago, and we both said the same thing, so it was kind of cool. And I guess the general point here is that simultaneity is a thing that doesn't exist. And so we should stop building systems that assume that it does just because it makes programming easier. We should devote efforts into building better languages. And so I challenge you to build better languages. Thank you.